a huge idea today. We are going to see two things by the end of class today. We're going to see how do antiderivatives and integrals link together, because they're clearly related. Like, we've seen that we get some of the same stuff. Or if you haven't noticed it, I'm spoiling that for you. But beyond that, these problems, it's really quick and easy to find an integral, right? No, it kind of sucks, right? Like, it's long, it's tedious, the problems can be gross. There's worse things out there, but don't know that you guys have really done much worse than finding an integral by the limit of the Riemann sums. The good news is today we stop. We get a shortcut. Okay, so here we go. Let's jump in. Today we start 5.3, and I told you I'd put a little fun in class for us, and you got it. We're looking at the fundamental. Got him. Theorem of calculus. Okay. Now, for this, it drives me crazy your book doesn't do this, so I'm going to. This is not necessarily part one of a lesson. The fundamental theorem has two parts to it. So when I say part one, that's just going to be our initial focus. Okay. I lied. Scratch that. We don't have to erase it, but I am going to give you both. I just thought I would separate it here, but I don't need to do it here. Okay. My bad. Quick check. What do you think the shorthand that's going to be commonly accepted is for fundamental theorem of calculus? FTC. Good call. You should write FTC. We're going to define this. FTC. Fundamental theorem of calculus. Now, for these, there are only two parts to it, and we're going to use both of them. And I'm going to be honest, when I learned calculus the first time, part two, didn't really see the value in it. We will see the value in it. It's awesome. Everything gets so much nicer than it has been. So check this out. This breaks into two parts. So FTC, two parts. Now, the first part, or part one, if you'd rather, this is our shortcut. This is how we're going to save tens of minutes or 20s of minutes, depending on how gross the problem is, for every integral that we have to work out. We're going to be kind of rigorous and formal with this. And we'll start by saying let f be continuous on some closed interval for x in a to b. Okay, continuous function. There we go. Now, we'll say that a function, or the function, and I don't like the notation that they use, but I'm going to use the book's notation so it matches. There's a function that we're going to call capital I that is given as I of x, and we're told that this is exactly equal to the integral from a to x of f of t dt. Okay, don't love that they use I here, but your book does it. Okay, and beyond this, the function, this thing that's given by this integral, is also continuous and differentiable. And differentiable. Okay. Pause, just to make sure we're cool. When we first started finding derivatives, do you guys remember, like, the very first derivatives that we did, we just got numbers out of the deal. And then once we started learning shortcuts, rather than just taking the limit of the difference quotient, that f of x plus h thing, we, instead of just getting a specific number, all of a sudden we started getting functions out. And the derivative represented a function where if I want to know the slope at any point, I just plug in x. We now have a new function that instead of the derivative, it's just defined as the integral. So we've done something very similar. Notationally, it's ugly, but we have been doing this all year long. We went from derivative at a point to the derivative as a function. We are going from the integral at some range to a function over that same range. That's it. Now, as we're doing this, beyond this, we're going to say more so, and here is the big part of the fundamental theorem, part one. If I wanted to undo an integral, and I had my parts mixed up, but that's okay. What do you think? Have we seen anything that goes the opposite direction? Like, differentiating goes this way. What goes this way? Anti-differentiation. Okay, so if I were to take the derivative of the left side, the algebra says, hey, you're allowed to do this so long as you also take the derivative of what? Can we say the other side or the right side? Now, I don't have a good prime notation. We're not going to use prime, but if only we had a way to say we're going to take the derivative with respect to x. d dx. Okay, we're going to take the derivative of both sides. And let's see what we get out of this. F of t dt. And do we need to, I'm just going to let it ride for now. Never mind. Okay, for this, any gut feeling on what happens here? Like there's a bunch of weird stuff with the t's and the x's and stuff, and I get that. Does anybody have an intuition? Just shout it out. Don't care if you're right or wrong. What do you think we're about to write? One more time. The integral will go away. That's a good thought. Knowing the integral goes away, any thoughts then? So I'm just going to pretend, don't erase yours, but I'm just going to show you. I like Rafa's suggesting. He says, hey, I think the integral is going to go away. And you may just be left with what's inside, right? Now, for this, there's some bigger pieces going on here that we'll play around with as well. What's the upper limit of integration? X. So I see that it's f of t dt, but eventually I get an x in there. And this one is super nice. This turns out they do, as Rafa suggested, simply undo each other. F of x. Okay, we're going to put this into simple words and without all the t's and dt's and stuff. If you take the derivative of an integral, what happens? You're left with only the function that you were integrating, right? The integrand comes out with whatever variable we had here. Okay, is there, I'm okay with this for now. We're going to get like some bigger stuff here. Big takeaway, and we're going to make this wordy. If you want a derivative undoes a definite integral. Okay, this is a really important idea. They just undo each other. And we've already kind of started alluding to that when we differentiate to get acceleration and velocity, and we anti-differentiate to go the other way. These ideas are already there. We're just clarifying. Okay, now we'll see that this one, and I had my parts mixed up. This one, for me, is the harder of the two, but that's not going to be wildly difficult. Especially, just remember, always kick back to, we just did the limit of the Riemann sums as n goes to infinity. This is not difficult in comparison yet. Okay, don't know that it will be, but let's get part two, because this is the one that's really going to save us time. Part two, this one's our shortcut, and I'm sorry that I had them goofed up. Okay, here we go. F, we're going to do the same thing. Let F be continuous on A to B. And right off the bat, my first question is, with your neighbor, I'm going to give you like 30 seconds. What's different about how we started part two compared with part one? Like there's a fundamental, not necessarily the choice of that word. There's a huge important difference between how we started part one and part two. Well, let me see if you deserve the high five. What is it? So I have the same thing. I just didn't write it. Like, you're right. That is different. But it's on your second line that I see. Something fundamentally different. What do you think?
You said there's no X in the set of the.
So I agree with you that is a poor decision by me, because there could be. Okay, just real quick, I want to specify. I did not say X is in this interval. That's because I assumed it. That is not the difference I'm after. But you're right, that is different. You can put X's in the closed interval from A to B. I want a different distinction between the two. And I'll even change this so it looks the same so that we don't try to do that one again. What do I say F has to be on part two? Continuous. For part one, what do we say it had to be? Continuous and differentiable. I'm not speaking at all to the differentiability of this function because we're not going to use it. Okay, all that we have is only continuous. I don't care if it's differentiable. Doesn't matter to me. So as we're looking at this, here we go. If I'm going to write cap F And we're going to say what this means, but have we seen cap f before? What is cap f? Good. If cap f is the antiderivative of, we'll say lowercase f, because that's how our notation works, on this entire interval, or for all x in that same interval, if we're being more specific with it, then, and notice, no matter where you are, I would encourage a line break, because this is going to be arguably the most important thing that you're going to write in a while. Like, we're going to do examples with it, but this idea is fundamental. Okay. If before, when we worked this out, if I did the integral from a to b of f of x dx, before today, we had to work out everything, right? We had to say it's a limit as n approaches infinity of the Riemann sum from 1 to n, and then we had to work out all that stuff, right? Delta x, c sub i's, and f of c sub i's. And it's doable, but it's really taxing. Okay, turns out there's a shortcut for this. And we're going to look at the notation very carefully here. It turns out that this is easy to calculate. In this one, notice my bound is a number, a to b. I'm not going a to x anymore. I'm not making a new function. I'm just going to get a number like we have been. Okay, it turns out if we connect these back and forth, what's the integral is kind of related to another idea that we've talked about. And we even said it multiple times today. Before we said, let's take the integral, I might have asked you to find the something. Antiderivative is how this started. And check it out. It turns out that as long as we can find an antiderivative, we call cap f, we're going to use a new notation today that you guys probably haven't seen. We're going to draw, say it's the antiderivative, and we'll label these things. But then the common notation is that we just use a vertical bar right here for a second, and we just put a and b on here. Okay, now there's one more step that we're going to do, and there's going to be an equals thing, because this probably doesn't mean much to you. Real quickly, though, remind me, what is this? F of x? The cap f of x? The antiderivative. I'm just going to call it anti for my notes, because that's like a 12-letter word. Okay. Now, where do the a and b come from? The lower and upper bounds, or the interval. Like, I would take either of them. And check it out. This notation is pretty common. I've seen it in like every textbook that I've ever used, but there might be others out there. What's the upper limit of integration? So here we go. We're just simply going to do f, you are right, by the way, f of b minus cap f of a. This is our shortcut. Now, it is super handy with one thing in mind. The hardest part of being able to do these, and I think arguably it's going to be the hardest part of derivatives. If somebody struggled with derivatives, do you think, and many, like most of you have at one point or another, and I've seen it happen, everybody struggles with them at one point. It's okay. But when you struggled with derivatives, what do you think was the one thing that led to you getting them wrong? And there might be a bunch of answers. I have no idea what I'm really expecting of you guys. I want you to talk 60 seconds. When you get derivatives wrong, why do you think you get them wrong? Talk it out, 60 seconds. We're going to do a couple together, and then I'm going to have you guys get up and do some stuff at the board, but I want a couple in our notes first, I think. Okay, so we're going to use part 2 right now. And let's do that. So use part 2 of FTC. And I think I have a suggestion for this. So we don't have to keep saying part 2 or part 1 of fundamental theorem of calculus. I'm just going to start saying FTC sub 2. That's part 2 of the fundamental theorem of calculus. What subscript would I use for part 1? Deal. FTC sub 1. Cool. Okay, so let's do this to evaluate some integrals. And we'll start with super hard or super easy? Okay, fine. All right, so let's check it. For our first one, here we go. I want us to find the integral from 3 to 5 of x squared dx. And we're going to pause right here for just a second. I'm going to get A and B up on the board. I want you to have them in your notes as well, but we're going to be working them on the board. And I'm going to leave it up to you. If the people that are like speaking and stuff want to write the problems down in their notes, I think it's a good idea. But we're going to get up and do a little bit of movement stuff. Cool. So A, you guys will be doing these. B, you guys, I want to evaluate the integral from 1 to 2 of 4x cubed minus 6x plus 5 with respect to x. All right. For future iterations of this, I'm going to let random groups generate. But for right now, we have 13, 12 people in here. We have 13. I want 3 groups of 3 and a group of 4. You get 30 seconds to find your group. Cool. Once you have a group, pick a whiteboard up here behind me. We can write on this one as well. Okay. If you want these examples in your notes, your notebook should go with you. Your job right now is, with what we have about the fundamental theorem of calculus and how great of a memory you guys all have for how to calculate antiderivatives, everything can be gone. Yep. Your job, I want to see what you try. I want you to integrate these two. Find me those integrals with what is in your notes. Talk it out. It's a good question. That I'm going to ask you for the answer to here in about 3 minutes. The integral from 3 to 5 of x squared. What are you typing? Okay, you're good. You're good. I just making sure you weren't actually just typing the integral. Like, you're good. I want you guys to add the bar. Like, use the same notation that we used. Five cubed is 125. I'm just making sure because I see people